This is a clean glean on curvature. Here we're looking at the graph of a function y equal f of x. We have two circles drawn to represent the curvature at a given point. The circle on the left is of a larger radius compared with the circle on the right. When the circle, the inscribed circle, has a smaller radius, the curvature will be greater. For a straight line, the curvature will turn out to be 0. Let's look at a precise definition of curvature. If we start with a smooth curve given by arc length parameterization, the notion of curvature is a scalar found by taking the magnitude of the rate of change of the unit tangent vector. All right, that's a precise definition. Let's open up the book and look at this nice paragraph here. And we could note that this precise definition turns out to not be very useful, and that largely has to do with it requires arc length parameterization, and arc length parameterization can lead to tedious computations. So next, we'll instead look for various formulas, alternate formulas for computing out curvature. And there will be 3. Let's start with 315. Do a proof. 315 is going to be established by using the chain rule. Here we're looking at a derivative of the unit tangent with respect to any parameterization. If you recall, the arc length function is s of t. S then depends on the parameterization t, and this chain rule computation makes sense. On the right-hand side, let's go ahead and isolate out the derivative of the unit tangent with respect to arc length, as that was given as the precise definition of kappa. But since kappa is a scalar valued function, we'll need to take the magnitude of both sides. Nice. So we have our second equation. And looking at kappa, kappa is exactly defined as this left-hand side in our second equation. Then noting that ds dt, remember that the arc length function s of t is an integral, and the integrand is precisely the magnitude of a derivative on position function. Thus, we can swap out the ds dt, which is just a scalar, with the magnitude notation, and that finishes 315. Excellent. Let's then go on to 316. And then before we do, let's pause for a second and recall this notion of the unit tangent vector. Well, the unit tangent vector is a vector, therefore it has a direction. The direction is in the direction of a derivative on position, but it's also the unit tangent vector, and so it's a unit vector, which means that we take the derivative of position and normalize it. Then, thinking back, this unit part is what is most important, since a vector, which is of constant magnitude, will be orthogonal to its derivative. Well, the unit tangent is a unit vector. It's always of magnitude 1, and thus it's orthogonal to its derivative. Nice. So this is going to be an important notion that we'll come to later in the video. But for the moment, we can use that to define 2 more unit vectors. The unit normal vector, denoted by n-vec, is in the direction of a derivative on the unit tangent vector, but as we desire it to be a unit vector, we normalize it. Now, as we just saw, t prime vec is orthogonal to t-vec, Thus, the unit tangent vector and the unit normal vector are orthogonal vectors. So these two vectors here in this cross product are themselves orthogonal. You know that the cross product of two vectors is a vector that is orthogonal to each factor vector. All right, so immediately we're going to need this unit normal vector to establish our second alternative formula for curvature, 316. Let's go ahead and dive in. So the proof. All right, so we just reviewed the notion of the unit tangent vector. It is the derivative normalized. And we saw earlier that ds dt is, well, that's a derivative on an integral with integrand, the norm of r prime vec. And so ds dt is the norm of r prime vec. Now, with that, we can see that the tangent vector r prime vec is the same direction as the unit tangent vector, but scaled by ds dt. All right, good. Now, we're going to work with this identity here. The first thing that we'll do is we'll take a derivative of this identity. And then in taking that derivative, we're taking the derivative with respect to the parameter t. And since by this identity, the r prime vec is a product, it's a scalar product of the unit tangent vector, we come up with two pieces. So we have to look at the derivative hitting ds dt. And then second, we have to look at the derivative hitting the unit tangent. So this is r double prime vec. Nice. Glance up above at the equation 316 and we see that we want to compute the cross product of these two quantities. So we go ahead and we do that. Taking the cross product results in this notation. To evaluate this notation is to distribute the vector on the left to the vector on the right, which is a sum. And then we result in a sum of cross products. Nice. Note carefully how the scalars have collected to the front. All right. Well, something nice happens. The first cross product we see is the cross product of a vector with itself. And the cross product of a vector with itself is the zero vector, as the cross product tests for whether or not vectors are parallel. Thus, we can ignore this term and simplify our expression for the cross product of r prime vec with r double prime vec as this scalar ds dt, recall ds dt, on this cross product. Again, glance up at 316. We've arrived at a simple formulation of the cross product, but 316 requires the norm. Now, if we look at the norm of the vector we're trying to compute, it's the norm of a cross product. So remember that the magnitude of a cross product can be associated with the area of a parallelogram, and as such, it has a nice formulation. But recall, the unit tangent and its derivative are orthogonal. And because they are orthogonal, we know that the angle between them is pi over 2. Therefore, sine of pi over 2 is going to yield 1. And then the norm of a unit vector is 1. So the norm of this cross product is simplified to just the norm of t prime. All right. So now what we want to do is we want to isolate the blue highlighted term, as that's going to allow us to apply the alternate formula 315. In red, we're making a swap for dSdt with the norm of r prime vec. And then recalling 315, we need to add in one more copy in the denominator of the norm of r prime vec, so that that quotient highlighted in the red box is by 315 kappa, and then highlighted in blue is the formula in 316. And thus we've finished 316, and note that we relied on 315. Nice. This pattern is going to be repeated as we now look to 317. This third formula is going to be an application of the second formula. Let's go ahead and do that. Note that 317 starts off with if c is the graph of a function y equal f of x. So our proof, that's where we begin. That we assume that we have a plane curve, which is the graph of a function. These notions of curvature kappa rely on vector notation. So let's swap our graph of a function into a vector equation. And here the book is making use of the identity that the parameter t is taken to be the independent variable x. Note as well that to be a plane curve, we want nothing in the k direction. We want to stay in the xy plane. So trivially, we can accomplish a 3-vec by setting the scalar function on k-vec to be 0. In doing so, we are then able to take advantage of 316. All right, well, what do we need in 316? We need r prime vec and we need r double prime vec. Look at the position function. The derivative of x is 1. The derivative of f is f prime. Repeat. Compute r double prime vec. Nice. To employ 316, we need the cross product. Go ahead and form that up. And then looking at this computation, everything will go to 0 except for the scalar on k-vec. Here I've highlighted the 4 terms needed to compute that scalar. And you simply have the diagonal 1 times f double prime as the scalar function. Good. Well, quote 316 here, and then we have highlighted in blue that vector is simply f double prime on k-vec. K-vec is a unit vector, thus that norm will simply be f double prime. Look down in the bottom, r prime, we've already computed that, and thus computing its norm results in this sum. And looking at the formula 317, highlighted in blue is exactly that formula 317, again because we're letting y equal f. And then highlighted in the red box is exactly the definition, or the formula 316. Excellent. That establishes these 3 alternate forms of computing curvature. In computing 315, this derivative, this numerator, on the unit tangent, remember that the unit tangent is a normalization of the derivative on position. By being a normalization, this will most likely involve a quotient rule, considering evaluating a quotient rule derivative versus a straight derivative. 316 will likely be more appealing as easy computations than 315. So in practice, you'll find that 316 and 317 are more likely to be used. Note as well that 316 is particular for a space curve, 317 is particular for a plane curve, whereas 315 applies to any curve. Nice. Here's an assignment for you. Compute the curvature of this helix. An example is done in the book where specific values for r, I believe it's 4, and k, I believe it's 5, are given. And then this is just done in generality where r is positive and k is not 0. Nice. Okay. Earlier, we made these definitions for the normal and binormal vector. In the proof that we just gave of the alternate forms, we saw that this cross product defining the binormal vector is itself a unit vector. So we have two more unit vectors in addition to the unit tangent vector. We know that the unit tangent and the unit normal are orthogonal, and the binormal, being taken as the cross product, is itself orthogonal. So these three vectors are mutually orthogonal. So here's a nice picture. And what's going on is that at any point that you pick, and you want to think about picking a point on a curve, that you're reproducing the xy coordinate system, that you have copies of i-vec corresponding with t-vec, copy of j-vec corresponding with n-vec, and a copy of k-vec corresponding with b-vec. Let's take a look. We can look at this applet in GeoGebra. There's a link in the description to this applet. And then this applet is showing the TNB frame, or the Frenet reference frame. And they use, by default, a helix. Let's look at the graph that they produce. So here's that graph. In this graph, this is a three-dimensional graph. We have the purple curve, that's C. There is the position vector here in black, pointing to a point in red on the curve. That there is the direction of the curve given by the tangent vector. Again, think of that as the i-vec. And then there's the normal direction given by n-vec. Think of this as j-vec. And then there's the binormal direction given by b-vec. Think of that as a copy of k-vec. Let's watch this taken from different vantage points. This is in the first octant view, and then twisting around to get a better view. And then let's pause the video and then highlight in the circle, now sketched in blue. And this circle has a nice name. It's called an oscillating circle. That this circle is sketched in the plane determined by the tangent vector and the normal vector containing that red dot. And then that plane is called the osculating plane. And if we go and we plot in this osculating plane a clearer picture of this circle. So the circle is passing through the point P. The circle is sketched in the osculating plane. And then how big of a circle do we want to sketch so that the circle is called the oscillating circle? We let the circle have radius r, 1 over curvature. And then the r is termed the radius of curvature. And then such a circle is called an osculating circle. So at the beginning of the video, we were looking at inscribed circles. Those were osculating circles. And they are there to give you a visual on the curvature of C at a point P. And this should make sense if we appreciate that a circle has constant curvature. Nice. So here's an assignment. Show that a circle of radius r, taken to be some constant a, has curvature 1 over a at every point, i.e. that it's of constant curvature. Nice. And then another example. This one is a checkpoint problem taken from the book. Here is a plane curve. You want to find a point on this plane curve at x equal 1. Second, you want to compute kappa using the alternate formula stated here. Third, you want to find a center for the osculating circle, I've denoted that C at h comma k. You want to start at P, which is contained in the osculating circle, move in the direction of the normal vector, and then the distance that you move is the radius of curvature. Now, finally, with those pieces, you can plug into the equation of a circle and have produced an osculating circle for this curve at the specified point. Very nice. This was a clean glean on curvature.